Hello, I'm Chili, and this is my wife. Now, this is part 3 of the SSE hand relief. Very nice. That is probably the worst Borat impression you will ever hear. So at least you've got that out of your way now. You can cross that off the bucket list. Okay. So first thing is first, before we get started, what we need to do is we need to go to Team Explorer. You want to synchronize with the old repo, and then you want to make a new branch, and you want to create a new branch off of Origin Tint Your Taint, which I'm personally very proud of that name. Next, what you're going to want to do is you're going to want to listen to the smooth stylings of Chili as he regales you with SSE nuggets of golden wisdom. I made diagrams. And by made diagrams, I mean I stole them off the internet, which is actually way better for you, because I suck at drawing diagrams. And drawing in general. It's just not my forte. So what are we going to be doing today? Well, the title of this is the SIMD Shuffle. We're going to be doing a little bit of the tint and shuffle, as I call it. It's not quite like the slap and tickle, but it's kind of close. So the two operations we're going to be working with is tint, which is basically to tint an image with a color. And the other one is blend, if I can get it in here. Blend. And that's just blending two images together based on some alpha value, weighting between the two images. So for tinting, these are both basically operations of alpha blending, right? Now let me take a look at. So you've got your basic alpha blending formula here for integers. You multiply one color by your alpha value, you multiply your other color by the complement of your alpha value, or 255 minus alpha if you're working with byte values, which we are, and you divide by 256. Why? Because it's way cheaper than dividing by 255. Now, in the situation of fading, color 2 was black, which is 0. And that's not discrimination, it's just a fact. And so, what you get is you get this term cancels out, and you end up basically just multiplying by alpha and then dividing by 256. Now, with the tint, you can't do that. That simplification is not available to us. With alpha, we've got one value which changes per pixel. That's per pixel. And then we've got another value which is a constant. And we can still make a little bit of, I guess we can make some use of the fact that this is a constant to provide some optimization, but we can't just cancel the whole damn thing out like we did with fade. So how do we handle tinting? All right, so tint, here's the basic idea. We're iterating through all the pixels in the buffer. And what we're doing is, we're doing the same thing as the formula, right? We're multiplying by alpha here. C is the color that we're tinting. D is the destination color. That's the pixel on the image that we're tinting. And we multiply color by alpha. We multiply the pixel that we're actually tinting by the complement of alpha. We divide by 256. We do that for all three channels. We pack them together and we put that onto the image. Now this works, and as we've shown before, using the unions like this, very slow. Not very good. So the better thing to do is to shift and mask. And by shifting and masking, we can avoid the compiler shitting the bed. And we get a faster result. Now, pre-computing is even faster. We can note that this value of the color, the tint color times the tint alpha, is going to be the same for every single pixel in the image. So we pull that out and we pre-compute that outside of the loop. And then we blend as usual. And that is even faster, I think. Let me check. Tint shift and tint pre-computed. So let's take a look at and gain all together for you. Nice. So, very nice. Oh, I told you that was the last time you're going to hear that, and I lied. All right, so there you go. You got your red tinting goodness. Let's look at the log file. So that's 2.6 milliseconds. And if we go tint pre-computed, we'll run that. Yeah, we can change the alpha. We control the horizontal. We control the vertical. Yeah, that's faster. That's quite a bit faster. So the compiler is not smart enough to pull that that operation out of the loop. We have to do that ourselves. And indeed, that is what we did with tint pre-computed. And tint pre-computed packed, all that does is here we have the pre-computed channels and we add them channel-wise and then pack the results. Here we pre-pack the pre-computed channels and we add them in afterwards because we realize that by alpha blending the scaled source and destination colors, they won't overflow. They won't add up to, the channel values won't add up to more than 255 if we've done it correctly, right? Because we're multiplying by 255 and 1 minus 255, and we're also dividing by 256. So overall, they shouldn't overflow, so we can just add them directly here. Again, we've done this before, and this is all known. Tint half packed is, again, we do the packed thing, except now we also divide by 2 by shifting the whole packed value. And in order to prevent the ones from leaking into adjacent channels, we mask with this mask here. And again, that works very nicely. Okay, so that's all the tint bullshit that you have to know. Let's get on to the fun stuff, which is how do we do that in SSE? So we gotta scroll all the way down till we get down to the SSE. So tint SSE. Here's where the magic happens. Now I'm not gonna go over this because you already know what this loop is doing. We're looping by pointer here. And here we're just setting up some constants, 1, 0, and this is 255, right? In 16-bit values. And this constant is the color. And we're setting the color in all 4 of the packed 32-bit values. And so what we do is we load the destination pixels. Then we unpack them. I've talked about unpacking before, I think. Yeah, I did that. And we're also going to unpack color. And we want to broadcast the alpha values so that they match up with the with the color components in the destination pixel. So what we want to do is we want to multiply our color components by alpha values. We want to multiply it down like this. The problem is that our alpha value is stuck in the top of this 4-channel color. So what we want to do is we want to broadcast this alpha into all the channel positions here like this, and then we can multiply our color by the alpha. Now, I mean, it depends on what we're multiplying. If it's the pixel that we're multiplying, then we want to multiply it by 255 minus alpha. But the same idea holds that we want to get the alpha value from this position into these positions. And the thing that we use to do that is called a shuffle instruction. This allows us to rearrange the values in the vector register. So shuffle low, shuffle high. What do we do? How do we do? The way you do it is you do it half and half, the top and the low part. So let's look at the low part first. This would be shuffle low. Basically what you have here is you have 4 multiplexers, and they can select any one of these 4 values, and each one of them can select that value and put it in its corresponding destination position in the register. Now the way you select this is the 4 values you can choose. So that means that you use a 2-bit value to select. So obviously 0, 0 is going to be this one. This would be 0, 0. This would be 0, 1, 1, 0, and 1, 1. And using this situation, you can rearrange these 4 sources into the destinations. Now the beauty of shuffling is you don't have to, the idea when you think about shuffling a deck of cards, you think of rearranging the order, but you don't have to maintain the same elements just in a different order. You can copy, so you can use, for example, 0, 0, 0, 0, 0, 0, 0, 0, and that will copy the value A into all 4 of these positions. So shuffle is not only a shuffle instruction, it's also a broadcasting instruction. And shuffle low will allow us to rearrange the low 4 elements, and shuffle high will allow us to rearrange the 4 high elements. Now you might ask yourself, why don't you just make a single instruction that allows you to rearrange them all at once? And that would be nice, but there's a problem. And the problem is that when you use shuffle, you have to specify an immediate value that the instruction bakes inside of itself to determine how the rearrangement is going to be happening. And that value can only be 8 bits. The immediate value for SSE instructions, maximum 8 bits, as far as I know. And if you, a little quick math, you need 2 bits for each one. You're using up all 8 bits right here. So that's why you have shuffle high, shuffle low. For the 32-bit shuffle, there is just shuffle. There is no high or low because 32 bits, there's only 4 32-bit values in an SSE register. So you don't need high and low. You can do it all with one instruction. But with the 16-bit shuffles, you need high and low. And because of that, you can't cross from here to here. You can't shuffle a value from here to here. It doesn't work. So you'd have to do, if you want to shuffle across the lane, as they say, cross lane operation, you have got to do more annoying bullshit. Like, for example, shuffling with the 32-bit shuffle to cross, and then shuffling with the 16-bit to get it to where you want in the 16-bit. It's kind of annoying, but that is how we do. So with this one, what we're doing is alpha is equal to shuffle low, color 16. So we're broadcasting the top element in the low part of color 16 to all 4 areas. We're broadcasting the alpha to all 4 components in the low half of alpha, with the source being the color that we are tinting with, right? So we're broadcasting the alpha from the tint color in the low parts. Then we're going to do the same in the high parts. Now we subtract the alpha from the 255 values, the ones, as I say. I call it ones because in binary it's all ones, right? We subtract alpha from that to get the complement. And now we have the complement. We can multiply the complement by our pixel to get the multiplication. We can multiply the alpha by our original color. Then we can add them together, high and low. Note that in color, high and low are the same, right? There's only one color, so we don't have to do high and low. We just do color. And then what do we do? Then we shift to divide by 256, and then we pack and store. Simple, not too difficult, I hope. This macro here, this is a macro, and it generates those values. Let me just see, it doesn't tell me the result. It generates the 8-bit value immediate that the shuffle instruction needs. So this one would generate 255, I believe, because it's just 1 1 1 1 1 1 1 1, right? But it's easier than writing it out, you know, in like hexadecimal. It's more readable. I believe Visual Studio 2015 supports now binary literals, but I don't have that yet. So, anyways, just use Shuffle. It's a good macro. All right. So that's Tint SSE. Now the problem with that is, of course, in here we are multiplying, again, we're multiplying the alpha by the color, and we are shuffling the alpha out, we're multiplying it by the color every single pixel, but that never changes. So what we can do is we can do that bullshit up here, and then all we've got to do is just add, where is it? Yeah, we just add the result of all this bullshit. So we pre-broadcast the alpha, we pre-multiply, we pre-divide, and we pre-pack it. And then all we have to do is just add the packed values. Because like I said before, we're not going to get any overflow because everything's been scaled already. So there should never be any overflow. So this is basically analogous to, you know, our packed version, which is standard code, x86 code. And this one, so here we have Tint SSE, and here we have Tint pre-computed. So let's check the performance. Tint SSE. Take a look at that. Works. And the performance is, no, that's not it. So, you know, 260 milliseconds. Okay. I mean, it's obviously better than what we were doing before without SSE. Let's try Tint SSE pre-computed. That's not the name of the, that's not the name of the function. Let's go back. Come on. Where is your print tcomp? Okay, whatever. Fuck. Yeah, I got you. I got the names backwards though. Pre-computed SSE. There we go. Build. Run. And again, works like a charm. Yes. So before we were at 260, now we are at 250. So barely any change. And you might be asking yourself, well, surely that doesn't make any sense. It does if you look at the disassembly. I'm not going to do it here, but if memory serves me correctly, basically the compiler was smart enough to pull this bullshit out from here, and when it compiled this to machine code, which it could not do, strangely enough, in just the standard C code, but it was able to do it when we built with intrinsics. Just weird stuff. You can't really predict when the compiler is gonna, you know, go all MVP on you and when it's gonna shit the bed. As always, you gotta benchmark where it's important. Can't take anything for granted. All right, now the next thing we can try is Tint half SSE using the averaging function. And that's if we are ensured a 50-50 value of tinting with the color, then all we need to do is call average EPU8, and that's super fast. This is better than before when we were calling average EPU8. We were just calling it with the 0. We were using it as a bastardized divide by 2 in 8 bits. Now we're actually utilizing its potential a little better. We're actually doing an average. That's all. If you do an alpha blend between two values with an alpha value of 127 or 128, you're basically just taking the average of the channels in the two values, the two images. So tint average half it's going to be fast. You can check it yourself. It's not important. What is important is that now we are going to move on to the second function I wanted to cover in this episode, which is blending. Now, blending it's like tinting. It's like fading in that it's an alpha blending function. But now we're taking the values of two images, the pixels, and we're blending them together. So now we don't have a constant color that we can pre-compute once for the whole operation. We have got to compute per pixel. Images changing per pixel. The only thing that doesn't change per pixel is the alpha value, because blending is just an operation blending based on some alpha, some weighting between the two images. How much do we want of image A? How much do we want of image B? So the alpha value doesn't change. So we can pre-calculate the alpha. We can use set 1 here. So, and I'm not like up here just for demonstration's sake. I did the shuffling, but we don't have to do the shuffling. We can just use set 1. Now, in general, and I wanted to talk about this. In general, inside of the loop where you're doing your actual processing, should not have any set 1 or set functions, because these are slow. They're very easy to understand, easy to write, but they're slow because what they do is they load a value into your register, into your standard x86 registers. Then they transfer it from those registers into the SSE registers, and then they shuffle. And that is slow. You don't want to be doing that for every single iteration. You want to be loading with SSE loads like, mm load and mm store. You don't want to be using set. But it's fine outside of the loop, obviously, because you're only doing it like once for all these operations. It's like over 1 million operations, right? So it's fine in here. It's not fine in here. That's all I wanted to say. So we set up the alpha. We set up the complement. We set 0. One exception is you can use set 0 inside of a loop. It's fine because set 0 just boils down to a single exclusive OR operation. If you exclusive OR any value with itself, the answer is always 0. So this just boils down to exclusive OR. It's super fast. So I use this all the time. But you never want to be using these set values inside of the functions. I've benchmarked it myself, and it is considerably slower. All right. So that out of the way, let's talk about Blendy. So what we're going to do is we're going to load the source pixels, we're going to load the destination pixels that we're blending from and we're blending to. We're going to unpack all those pixels to 16-bit values. Then we're going to multiply them by the alpha and the complement of the alpha. And then we're going to divide them. Then we're going to add them. And then we're going to repack them and store them. So that's it. It's very simple operation, but it's it takes more work than tinting. So we go blend SSE and shit. Okay, so I need another. I didn't do this here. I want another image. So I got Borat here. So we're going to add Borat to the... All right. So we're going to start with the B's, not the B's, and then we're going to blend on top of that Borat with the alpha value that we control with our mouse wheel. So here we go. Here it is. We can have the B's, not the B's, or we can have Borat. So that works very nice. Very nice. And we go to log file, and we see that this is a more expensive operation, obviously. It's taking on average, about from 500 to 600 milliseconds to blend two full screen 720p images. So the question is, can we improve this any? The answer is yes, we can. Yes. Where's the code? Here it is. All right. So the first thing that actually, this is not the first thing that will come to mind, but there's a little trick that I want to show you. It will make this code a little bit faster. You saw nothing. Okay, so we know that if we multiply two 16-bit values together, we can use the mul low function to give us the lower 16 bits of the result, and we can use the mul high to give us the high 16 bits. And mul high has two versions, by the way, unsigned and signed, because when you multiply two 16-bit values together, the low result is always the same, no matter if it's signed or unsigned, but the high result depends on whether it's signed or unsigned. It's weird. Don't worry about it. It's just, that's how it works. Okay. So multiply two 16-bit values together. In general, you get a 32-bit result. You can get the top and or the bottom with different operations. Now, here's a neat little thing. Multiply two numbers together, 16-bit values, where the low 8 bits are 0. What's it going to look like? The low 16 bits are going to be 0, and the high 16 bits are going to have, some value in it, depending on what was in A and B. Now, multiply two 16-bit values together. One of the values, the high 8 bits, have something in it. The other one, the low 8 bits, have something in it. What do you get? Well, if A and B are the same between these two, you're going to get the result here shifted down by 8 bits. Now, this is kind of big, because what have we been doing so far? We've been multiplying two 8-bit values together. With mul low, we get a 16-bit value, and then we shift that by 8 to give us our divided by 256 value. If we multiply with mul high, and one of the values is in the top 8 bits instead of in the low 8 bits, what we get is our result pre-divided by 256, pre-shifted. So we can save ourselves a shift operation if we skew one of our values over and then use mul high. That's the trick. That's the joke. You suck, McBain. Okay. So that's what we're doing here. That's what blend SSE high is all about. It's all about, see here, alpha and the complement shifted to the left by 8 bits. And then we call mul high EPU 16. It's got to be unsigned. And then in the end, we do the same thing. We add and we pack. But this saves us from having to shift. It saves us these shift operations. Shift isn't a super expensive operation. It's pretty fast. But still, it's going to be a little bit of a gain. So let's try blend SSE milliseconds. Now we're gonna blend here. Yeah, that's good. And we're gonna go to the log file. Now we're getting 383. That is not an insignificant speed up. Over 20%, like 25% maybe. It's good. It's really good. Almost 25%. So it's not bad for a little simple trick. What else? Now, one little thing I want to show you, if I can remember where my code is. Here it is. Now AVX, I'm just going to do a little blurb on AVX. AVX is like SSE, only it works over 256 bits. And it's almost like executing two SSE instructions side by side, the same instruction side by side. And the funny thing is, you can basically take an SSE algorithm, a piece of code, a routine, if you will, and replace all the M128Is with M256Is, and replace all these MM128s with MM256s, and it just works. So it's almost the same stuff. It's all the same bullshit. Of course, you got some more constraints with respect to alignment stuff, because now you're working with data that's twice as wide. But in general, it just works. You can just basically do a copy and replace, and you're all good to go. So let's try with AVX. And we're gonna zoom in, zoom out. That's not what you call that, but that's the words that popped in my head. And we see that we get a little bit of a boost, but not as much as you'd expect. You're not getting a 2 times boost. And I think the main reason for that is probably we're already maxing out what our memory can handle, what our cache, the speed of our cache. So in this case, AVX not gonna be a big help. But I could be wrong. There could be other factors. Like, for example, we're building this code 32-bit. If we switch to 64-bit, if we switch to using all AVX, because you get penalties sometimes for mixing AVX and SSE together. So if we switched all our code, like if we go into here, properties, what the fuck? Properties? Configuration, here it is. And C++, code generation, and we switch this SSE2 to AVX2, telling the compiler you can use AVX, and then we don't call any SSE instructions, and we use x64, then it might be good. It's not, the problem isn't with mixing SSE and AVX, it's with mixing VEX and non-VEX instructions, but I won't get into that right now, it's not important. What is important is that AVX gives us a little boost, but not too much. And I wouldn't expect too much because we're already pushing the memory limit. So, what's next on the plate? Blend half average SSE. Okay, so here we're just blending two images half and half together. It's the same as tinting, except instead of using just a fixed color, we're now loading pixels from two different images, averaging them, and then storing them back into one of them. It's the same thing. It's going to be fast. I mean, it's going to be super fast. Let's just take a look. Blend half average SSE. Okay, yeah, we don't need an alpha value, obviously, because alpha is fixed. It's going to be 127 or 128 or whatever. 128, I guess. So yeah, we got a nice blend there. And if we look at our good friend Mr. Log file, 334, 315, yeah. So basically, we're maxing out our memory more than anything, and that's why that's why we can't get much better out of AVX. So blend alpha SSE. All right, so here's the last little section of my little ticketly talk. I don't know why I called it that. I don't know why I reverted to Mr. Ned Flanders. I don't even know why I called him Mr. I'm falling apart here. But So the way that the standard blend works is we're blending based on some constant fixed value that doesn't change between two images. But with blend alpha, we are now blending per pixel. So some parts of the image will be stronger and other parts can be weaker. And that can give you some nice effects, obviously, right? But it's also now we're adding more things that aren't fixed. So more processing has to happen per pixel. So let's take a look at what this looks at, because it looks pretty freaking sweet, if you ask me. So I've got an image with a proper alpha channel. It's called flare. So let's blend flare. And let's blend the flare alpha SSE high. So this is again using our trick of mole high with shifted values. As you can see, so here's our alpha image. We're blending that on top of another image. Most of it is just taking the source image, but some parts with the lens flare are strongly biased towards the alpha image, which is a lens flare. Okay, so I mean that's a neat effect, obviously. How expensive is it? It's pretty expensive. It's more expensive than standard blending two images without the optimization, right? So I'd say this is like maybe, I'm just pulling this number out of my ass because I don't want to pull out my calculator, maybe like 40% more expensive than our optimized version of the standard blend. Alpha blend is more expensive per pixel alpha. So how is it different? I mean, we get our 0, again, we get our 1s. This is more just for my own personal comfort. We load, of course, source destination. We got to unpack low and high from the source, unpack the destination. Then we broadcast the alpha. Now remember, because the alpha is now changing per pixel, we can't do it outside of the loop. We've got to broadcast every single pixel. And that's what's adding some of the extra length to this function. It's not giving us any girth, but it's giving us lots of length. We got to shuffle the low and the high. So I've put the shuffle low and the shuffle high into one instruction. So we call shuffle low, and the result of that will be the original source with the alpha values broadcast in the low and the high values remain unchanged. And then we shuffle the high values, and then what we get in the end is just a value with all the alpha values. So alpha low, where am I talking about? Source low contains 2 pixels. Source high contains 2 pixels. This shuffle will shuffle the alpha in the low pixel. This one will shuffle the alpha in the high pixel. And that's of the low 2 pixels. And then in the high 2 pixels, again, we shuffle the alpha in the low pixel and then the alpha in the high pixel. And what we get is we get alpha low, alpha high, each with 2 alpha values broadcast in 16 bits in the top and the low halves of the XMM register. Hope that makes sense. I don't want to draw a picture. And the complement is, again, we subtract from 255s. Then what we're doing here is we're shifting left by 8. And we're doing this in order to take advantage of our mole high bullshit. So we shift the source low and the source high by 8. And now we can, let me think here. We can do mole high and we get our results. So we don't have to shift down. Now there's a reason, remember before we didn't have to do any shifting whatsoever, but here we have to shift these values up for the source in order to take advantage of our bullshit. Now, the way it works is in the destination, notice how the unpack is switched. The 0 is now here and the destination pixels are here. And what this does is this will unpack it such that the channel values are in the high 8 bits instead of in the low 8 bits. It's weird. I fucking hate the way that Microsoft orders these what you call it, the parameters to these functions here. Because to me, I would think this would be the high 8 bits, this would be the low 8 bits, but no. Here, it's the low, these are the low 8 bits, these are the high 8 bits. So this is your standard unpack. You unpack your whatever you want into the low, and then you just put zeros in the high parts. This one, we switch it up. Now we're unpacking our values into the high 8 bits, and we're putting zeros in the low 8 bits. Now the reason why we don't do that for the source values is because we need them to be, what's the word I'm looking for? We can't have them all messed up because we have to shuffle the alpha values. Yeah. These alpha values have to be in the low 8 bits. So that means that these ones have to be in the low 8 bits. Because if we put them in the high 8 bits, then they will also be in the high 8 bits when we shuffle around these 16-bit values. So we can't have everything we want, and we have to do a little bit of shifting to get everything set up. But then we can multiply and add, and we can have a grand old time. And that is how babies are made. It's basically the same as standard blending, except that now we have to reshuffle the alpha values every time, every pixel. Now I'm going to show you some little bit of black magic that you would think does more than it actually does. So let's look at our good old friend Blend Alpha SSE High. No, wait, we did look at that, right? And it was slow, I believe. Let's take a look at game. Yeah, it's kind of slow. Log file. Yeah, like about 580 milliseconds slow. Slow enough. Slow enough, my friend. Let's go back down here and look at the next thing, which is Blend Alpha pre-multiplied. Now, this is something that I didn't think of when I first did the tutorials in the alpha blending section, way back in intermediate maybe, or maybe even beginner, I can't remember. But what you can do is if you have like an image, like a sprite, that you're blending, alpha blending onto a destination, instead of unpacking the alpha from that image and multiplying it in every time, you can do that ahead of time. So you can take you can take an image with an alpha channel, and you can scale the channels of the image by the alpha, pre-scale, pre-multiply it. And if you pre-multiply and divide, of course, by the alpha, then all you have to do is do the same for the destination when you're doing the actual processing, and then add them together. So what we do is we load source, we load destination, we unpack the source and the destination. And then what we do is, like normal, we shuffle the alpha values into place. We broadcast them to where all the channels are. But now all we have to do is multiply the destination by the what do you call it? The complement. Then we pack it together, and then we add that to the source directly, because the source is always already pre-multiplied. Again, we don't get any overflow. It's just like when we were doing the packed versions of Tinting, whatnot. So by pre-processing, by baking our images, we can save some processing time. And let's take a look at how much we save. Because we are cutting out, if you look at this compared to this, we're cutting out a lot of stuff. We're cutting out multiplies. Multiply is a slow operation. compared to the other ones we have here. So let's take a look. What is this called? Copy that. I should have been doing this the whole time. Paste it. Build. Run. Oh, it looks ugly. Why does it look ugly? Because I have not pre-multiplied the image. So we got to go here. Uncomment this line. Pre-multiply alpha. All pre-multiply does is it goes in here and it does the bullshit of scaling by the alpha value. And it also turns the alpha into the alpha complement, so we don't have to do that either. So it pre-scales by alpha, and then it pre-complements the alpha value. And then we have a baked surface. And if we bake our surface first, then we get a nice image. Very nice. And then if we look at this log file, we see that we barely get any speed up at all. We get a very little speed up. And you might be saying, Chili, that doesn't make sense. You've actually saved yourself quite a bit of bullshit here. Why isn't it much faster? Let's take a look at the situation. My situation is this. So if we've got some code like this, we expect it to execute these instructions one after another. So it moves the data, and then once that move is done, then it pushes it onto the stack, pushes EAX, call, move, does a multiplication here. Once that's done, it does a load. But that's not exactly how computers work these days. I think I just broke my computer. Okay, stop that. So computers are pipelined. And the reason for that is like an instruction, any instruction, it takes a number of operations to complete that instruction. You've got to fetch the instruction, you've got to execute it, you got to write the result back to memory, you got to decode the instruction. You got to figure out what those numbers are telling you what to do. And these instructions, all these operations, they take time. So let's say it takes 5 cycles to do an operation. So if you had 5 operations, you would imagine, okay, that's 25 cycles. But each of the steps in completing an instruction, these steps, let's say they're operating on different units inside of the CPU, different modules. So first, if you're executing instruction 1, you're going to do some processing in F, you're going to do some processing in D1, D2, EX, WB, and then the instruction's done. But that's kind of wasteful. Think about it. You do an operation in F, and then you move to do the next part in D1. F is just sitting there doing nothing. D2, still sitting there. D3 or EX, still sitting there. And then you can do another operation here. It's wasteful. You don't want to have all these units sitting around doing nothing. So what you do is you pipeline your instructions. You break them down into the steps that can be executed on different units. And then you do step 1 in F, and then step 2, D1. Now F is free. F starts the next instruction. So F is going to be working on instruction 2, D1 is working on instruction 1. Now that's done. Now D2 is working on instruction 1, D1 is working on instruction 2, and F is working on... Now I'm getting all confused. Just work with me here. It's all good. When you get to this point here, all these units are now going to be occupied doing some work. And instead of 5 instructions taking 25 cycles. Now they only take 1, 2, 3, 4, 5, 6, 7, 8, 9 cycles. And that, my friends, is very nice. So, what does this have to do with our pre-multiplication optimization not doing it for us? Well, every instruction here has two main performance values associated with it. And those values are the latency and the throughput. Now, the latency is how long it takes that instruction to finish. Basically, if you look at that in terms of the diagram I just had up, if I can find it, latency means the number of boxes here, basically. So it takes 5 cycles from the start of the instruction until the result of the instruction is available. Now, let's go back to our thing here. Throughput is how many of these it can execute per clock cycle, or the inverse of that. It's kind of complicated. I don't know why they give you the inverse, but basically a throughput of 1 means you can execute 1 multiply per clock cycle. So you can start a new multiplication instruction every single clock. So that's basically almost exactly like this diagram here. 1 instruction takes 5 cycles to complete, and you can start a new one every single clock cycle. So you get a situation like this. If you look at other instructions, let's go back here, like the one I had before, if I can get to it. And if I type in and, why do I get add? That's weird. Now and is very simple. It has a latency of 1, so its value is available almost immediately. It has a throughput of 0.33, which means, strangely enough, that it can do 3 of these operations every clock cycle. It can start 3 of them every clock cycle, and the result is available in the next clock cycle. So it's a super cheap instruction, whereas multiply is pretty expensive. If you want a really expensive one, then try mul packed single. Wait, that's fine. Okay, let's try what is it? Div packed single. So now this one has a latency of 14 and a throughput of 14. So you can, well, it depends obviously on the chip. But in Sandy Bridge, it's the worst, so I just picked that. So it takes 14 cycles for the value to appear, and you can get 1 instruction every 14 cycles. So there's almost no overlap. It's very slow. Division in floating point is very slow. So, that being said, what was I talking about? Okay. So the important thing, the 2 important values for an instruction are the latency and the throughput. Now, these values come into play in different situations. If you've got a situation where you're doing a calculation of x1 times y1, x2 times y2, x3 times y3. These can all happen at the same time. So you're mostly interested in the throughput. How many of these can I push per clock cycle? But if you're doing an operation like x1, like let's say this is z1 is equal to x1 times y1. Now if you're doing an operation like x1 is equal to x2 times x3, and then x4 is equal to x1 times x5, and then x6 is equal to x4 times x7. The numbers are weird, but you get the idea here. If you've got x2, x3, you multiply them together to get x1, and then you've got an x5, you multiply that with x1 to get x4, and then you've got an x7, you've got to multiply that by x4 to get x6. So you see here, the value of this operation here you can't get it until you've completed this operation. So now you're worried about the latency of this, the latency here, because your operations depend on the values that were subsequent to them, the subsequent operations. So this is latency bound. You've got a what's called a chain of dependency. And this makes code slow, because now instead of being able to issue one multiplication per clock cycle, you're basically limited to one every 5 clock cycles because you're waiting on these x values. Now that you understand this, take a look at the code again, and maybe you'll see why we didn't get much of a benefit from eliminating 2 multiplications here. Let's go back down to blend alpha pre-multiplied SSE high. Here we go. So in our standard blend alpha, we're doing 4 multiplies. We're doing 2 shifts and 4 multiplies here. In this one, 2 multiplies. So we've eliminated a couple of multiplies and maybe a couple of shifts as well. But shifting is super fast, so it doesn't really matter. Now, the thing about eliminating these multiplies is look at these 4 multiplies. Source low 16, alpha low. Source high, alpha high. Destination low, alpha low. Destination high, alpha high. And they're going into result, 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 result. If you notice, all of these 4 multiplications can happen in parallel. They don't depend on each other. So even if we eliminate 2 of them, they were happening almost in parallel anyways. So we didn't really eliminate anything from the dependency chain. We just eliminated 2 operations that were already happening in parallel. And that is why we don't get the speed up. And this is a very big thing in optimization, identifying dependency chains, operations that depend on each other, and trying to make those chains as short as possible. And the length of the chain is determined by not really by the number of instructions, but in the latency of the instructions. Latency adds to the length of the dependency chain. Throughput gives you more girth in your parallel execution of instructions that are not chained. It's the old length versus girth question. It's a one for the ages. But anyways, so that's the reason why pre-multiplied is not giving us the boost that we would have normally expected from eliminating, eliminating 2 multiplications and eliminating these shifts. It's kind of a disappointment. But it is what it is, as people say. I don't like that saying because it doesn't actually say anything. It's a tautology, right? It is what it is. Well, yeah, fuck, of course it is what it is. Are you fucking, ugh. Anyways, so now I'm going to show you something that will give us a speed up. And it is going to make use of a little something that I like to call SSE3. I didn't make it up myself. That's what it's called. It's actually really stupid. This isn't a typo. There is a SSE3, and then there is a SSE3. It's just don't get me started. But this will allow us to use one instruction called shuffle EPI8. And this allows us to shuffle 8-bit values across the whole register. It allows us to shuffle 16 8-bit values anywhere we want inside the register. Now this is beautiful because we don't have to do shuffle high, shuffle low anymore if we do this stuff. What we can do, let me just show you. We gotta have shuffle. Oh, there it is. So the instruction is P shuff B. Now if you remember what I said before, SSE is limited in that the immediate operand can only have 8 bits. And so, for example, that 8 bits would allow us to shuffle 4 values into 4 arbitrary positions. But now we're shuffling 16 values into 16 arbitrary positions. That's going to require a lot more bits, right? Every position is going to require 4 bits, right? 16 positions. And there's 16 values. So that's 16 times 16. Wait, no. 4 bits times 16. 4 times 16 is 32. So we need 64 bits. And that is not going to fit in our size that we have for immediate values. So what we do instead is we use an SSE register as a shuffle mask. And so all of our shuffle values are now held in another SSE register. So, for example, what is love, baby don't hurt me? No. What is 0D, 0A? Okay, I get this. So this is the mask. This is what's telling us what value to take from. So position 0 of the mask determines position, what is this? Oh, 0, okay. So position 0 of the mask determines what goes in position 0 in the destination. So position 0 in the mask says 9. So we look at position 9 in the source, FA. That's what goes in the destination. Do you get it? The top position of the mask says 0D. We look in D, it's a 65. We put a 65 in here. These ones all say 0A. So in these positions here, we're going to take the value from 0A and broadcast it in. That is the magic of, the instruction is called P shuff B, packed shuffle bytes, and the intrinsic is shuffle epi 8. And it's fucking sweet. It's just so good, and I can't even begin to tell you because there are other applications to this. The rabbit hole goes so deep you don't even know. But the basic important thing is that we can freely shuffle 8-bit values anywhere inside of here. The only cost is it takes a register to do it. And remember, whatchamacallit, SSE instructions, they only have a source and a destination register. So what it does is the destination is actually the mask. So by shuffling, you destroy the mask. These values get replaced with the shuffled values in here. The mask is destroyed every time you shuffle. So you've got to rebuild it every time. You got to recopy it, whatever. So that's one downside to P shuff B. But it's so good. It's good. It makes my dick so hard. Anyways, so by using this, we can save on shuffle high and shuffle low. We can do that all in a single operation. So here we got the source pixels. Now we've got to build our shuffle mask. Oh, one more thing I didn't tell you. It's not in this diagram. But values from 0 to 16, or basically it takes the low 4 bits, 0, 0, 0, 0. It takes the low 4 bits of every 8-bit value in the mask, and it uses that as the index for shuffling. But it also looks at the very top bit, so the very top 8th bit. And if that bit is set, it doesn't shuffle, it just sets the motherfucker to 0. So it also can selectively clear out areas, not just shuffle. Also clear. So good. Makes my dick so hard. So here we're going to shuffle. And these shuffles are for broadcasting the alpha to the places that we want. So 128, that's the top bit is set. We're clearing the top bytes, and we're setting the low bytes to the value of the alpha. So the alpha value is in the fourth byte, which is byte 3, right? Because we start from 0, 0, 1, 2, 3, and the 7th byte. And we are shuffling that inside. Right. So we're shuffling. What this lets us do is this lets us unpack and broadcast alpha at the same time, right? Because we're shuffling from packed pixel values. So from 4 pixels, which are packed into 8-bit channels, we are shuffling, unpacking by setting it 0 value, 0 value, 0 value. This is unpacking and broadcasting the alpha at the same motherfucking time. Unpack and broadcast at the same time. It's so good. So obviously we still have to unpack our channel values. So we unpack those. We unpack the destination. We load the source the way it is, right? Because we're dealing with pre-multiplied values. So we don't have to unpack. We just add the source. Destination. Yeah, we don't have to unpack the source. So we load the source, load the destination, unpack the destination. Then we shuffle unpack, so we broadcast unpack the alpha values. And these are the complemented runs, right? Because we've cooked this surface. Then all we have to do is do the mul high bullshit. We pack, we add, and we store. This is much less than this. And this, I'm not going to draw the diagrams because I don't have much time. I mean, I have all the time I want, but I don't want to make this video so goddamn long that you all die of old age before you finish it. So what I'm going to do is I'm going to be smart. I'm going to copy this. I'm going to paste it in here. I'm going to look at the performance we had, 5.5. Then I'm going to run this. Still same old G, you know me. And now we're down to 3.85. Very nice improvement in speed. But there is, one catch. And the catch is, where's my motherfucking... The catch is that this is SSE3, so somewhat old processors will not support it. So you have to check to see whether the processor supports SSE3 before you use any of these instructions. Otherwise, your program's just gonna shit the bed, obviously. Now, the way you do that is there is a special instruction on x86 computers called CPU ID. And what CPU ID does is it gets a bunch of dumb information about the CPU. All of what instruction sets it supports, the name of the vendor, and the name of maybe the brand. I don't know. It's all in here. Anyways, I didn't write this code. I just got it off of the MSDN and copied it into a CPP file and an H file. But you can use this code because I use it. And it's very nice. Very nice. It has one static instance, like a singleton, that it creates automatically in, where is it? In here, instruction set. And all you got to do is then just call instruction set blah, and you can get information about your CPU. So what I would do here is I would do something like if instructions, okay, that's not working. Let's change our strategy here. We're going to include CPU ID. Get rid of that and that. So, very simple. You can use this file whenever you want if you ever need it. It's not mine. I didn't make it. But yeah, if you're going to be using, I mean, you can basically assume that any processor supports SSE 1, which is, Pentium 3 and higher, and SSE 2, which is Pentium 4 and higher. If they're running shit on a Pentium 3 and it don't support SSE 2, it's just like, what are you doing with your life? So, but when you get up into like SSE 3, I've had people who couldn't run my code because the CPU that they're using doesn't support it. So you can't make assumptions like that, especially when you get up into like AVX and stuff like that. That shit, there's plenty of people who don't have CPUs that support that. So you got to check that stuff, and you check it. Well, you just use this class code, whatever. But anyways, that is all I want to talk about today. I think we've covered quite a bit. Dependency chains and instructions and bullshit. And this is all basically what this is I'm getting prepared for the Hugs series, where I'm going to make a very nice full screen bloom filter, all in software, all using SSE. Very fast, very beautiful. Make your dick so hard. Diamond dick, as they call it. But anyways. Oh man, I just zoned out there for a second. That's it for the episode, and I will see you soon. And the next one will be the last in this part of the SSE series. I might do another SSE series. I might do one especially covering floating point SSE. But the last one is going to be the end of the first arc of SSE. And then we'll see. But thanks for watching. I hope you learned something and enjoyed the video. And if you did, click the like button. It helps out a lot. Leave a comment, ask questions. You can ask questions on the forum, in the comments. It's all good. I will see you later.